Somebody was saying last night that their professor has office hours in
Did you?
They went down to
That way they don't have to deal with anyone coming in.
Yeah.
Do they really have to begin with it most of the time?
Yeah.
Especially since I work. I guess the only times I can think of that.
It's supposed to be at office hours at 7 a.m. Like, you're gonna have the excuse that, oh, I can't make your office hours.
True.
I'm just kidding.
That's who's not been showing up that late. Otherwise, I wish I could do more of that. Huh?
And they're two different cells.
So, congratulations with coming to an important milestone. We have completed boring theories, and we'll start something that is a little less boring, more related to real life, and less intense mathematically. So it will be a kind of break in sense, not that we will not do anything, but break in a sense that it will be easier and more intuitive. So for about a week and a half, you do not need to concentrate at your full strengths. Then it will come back to hard times, but as always. So we will have fun tonight at the lab. Please come if you want to practice MATLAB. And I would very appreciate if you can send your presentations by midnight on Thursday. So it will make our life easier for bringing things to the computer in a centralized way. Otherwise, if someone tell I needed to prepare until last minute, you just understand it completely, but then it will be a discomfort of loading and unloading. So sometimes in the next chapters we will keep discussing who we are and what we are doing, but now let's save this intriguing question for the future. And
Thank you.
slightly depart from the unpractical universe where there is nothing except one electron. We are looking to describe true materials and true molecules. And although our arsenal of tools is not super sharp, we already have enough skills to make first little connection to the real life. So this is just a list of presentations for Friday. I'm reminding it for myself, reminding to you. So the red ones, it is those who didn't vote, and I placed them there. So when we were torturing our young and sometimes not very young brains with free electron in the space, nothing was repelling electron and nothing was attracting it. Therefore, it was moving freely and expanding and moving constantly. But if you start thinking of true materials, there are positively charged who?
Proton.
Huh?
Proton.
Protons, ions of sodium, carbon, whatever, nucleus, ions, right? And electron is negative. Ions are positive, therefore they are attracted. What does it mean? If we are thinking in paradigm of one-dimensional picture, and it is not our goal to reduce everything to one dimension. It is just much easier and time-saving. So, in the free electron picture, the potential was always zero, right? Nothing was attracting our electron. But if you do have an ion at, let's say, position at zero, it means there will be something that attracts electron to this vicinity of potential, right? So we can formulate Coulomb law on the language of force or language of potential, that the positive ion exert on the negative electron. So same like least action principle. If I see a deep well, I will follow there. So electron will go there. And it is the main principle how atoms and molecules are constructed. Electrons attracted and forming this bound stuff. We are not ready to talk about atoms and small molecules, although they are smaller, but they are much more complicated for exact description. What we can do some more or less between quantitative and qualitative analysis of big collections of regular atoms that where we can neglect tiny details but get the main picture. So if we assume that there is a collection of several attractive nuclei in specific range of positions, let's say from x1 to x2, one can think of a range of space where electron feels much more comfortable to reside, because it will satisfy the least action principle. Like if I need to sit and nail something on the roof or lay in the basement of a coach, I will go to the coach. Same for the electron goes this lower level. And then if we do have ranges, if you have range of this limits of this interval, then electron probably doesn't mind jumping a little left or right, but as soon as it realizes there is a wall, that wall meaning it's just stop of this, I crawl to the end of the coach and I feel that it's not more comfortable anymore, and I better crawl in the opposite direction. So you've got the concept of particle in the box. Lazy person crawling between sides of the coach. How practical it is? It's probably not what you hear in other courses. And it is. It sounds a little far from chemistry and even physics and molecules. Is it a good concept? Well, we will pursue it anyway. We cannot decline because it is the only thing that we can do now. We are not trained enough to do something more complicated, but does it goes along with our common sense or with our growing understanding of processing in molecules. So let's discuss which realistic objects from a true life can be modeled by such concept. Like, what is a coach in the micro world? Which is there a coach molecule or whatever? Here, we can think that it is some attractive material, attractive collection of atoms, and outside is vacuum. Or it could be a material where electron doesn't want to go, something energetically unfavorable. But vacuum is good enough to assume, but it could be something different. Let's discuss. So, if you are not happy with the model object, raise the hand and ask questions. If you're happy, then please try to generate examples of molecules or maybe some materials that can be modeled with such concept. So do not hesitate, just share whatever comes to your mind. You can, if you're not sure, you can make a little recording of your first thought.
Would a metal network be a good way?
Metal network.
Like all metal like nuclei, because electrons love jumping through those.
Mm-hmm. So a chain of metal.
Yeah.
Okay, let's think of metal network. Not bad, it could be. Metal network. Chain. Yes, yes.
To be more general, maybe just any delocalized system.
Yes, and for example, which
Carbon nanotube would be easy.
okay, but carbon nanotube, where will be the walls of the box? It's not wrong, but just to help the rest of the class to follow you. Like nanotube is the tube of carbons, infinitely long or very, very long. And then there is something around. So which direction it is quantized, where electron can and cannot go.
The end of the tube would be the...
So the ends of the tube, but it also cannot go outside of the tube. So it's like more complicated than one dimension. Let's follow your idea about metal network and think about something that near and dear to each chemist. Does any of you makes research at related with conjugated polymers of photovoltaics? There are a couple of such research groups at the campus.
I mean, if you're talking like Rasmussen's group's research, I've heard of their stuff. I haven't dealt with it much yet.
Okay. So what have you heard about conjugated polymers?
Isn't it they're trying to make electron heavy areas of their like a polymer? I'm very
Yeah. I've learned about this materials not long.
the only time I've heard about it was at the regional meetings. And if I remember correctly, they Christine's stuff is like taking styrene or something and adding an electron heavy ligand to it or something to be able to accept take energy and throw electrons off at higher energy levels, if I remember correctly.
Yeah. So let me bring this idea because it doesn't deal with any exotic elements. It's all one can do this example with hydrocarbons, and one can synthesize them by means of. No. That's not right. That's not right. 2 arrows. Huh. There is a probably button N that I can push anytime. It's good. Good to know. I have a lot of space. Okay, let's keep this one. So, let's assume single, double. So, if by some reason we have a non-chemist in the audience, the dot means carbon, and tail means hydrogen. So let's assume that we have carbons, but they are not sp3 hybridized, but they are sp2 hybridized. Okay? So this language doesn't offend you. Good. sp2 hybridized. Which means each carbon wants to have 4 bonds, and now we have 1 to the hydrogen, and 1 to one neighbor carbon, 2 to another neighbor carbon. So in this situation, you do have, there is nothing specific telling that it should be double here and single here. So it could be jump double one from here to there, this double one to here, which means electron will move freely without anything preventing it from moving there. Right? Make sense? And then at the end of the chain, we tell, oh, okay, let's put hydrogen and hydrogen here, hydrogen there, which means and vacuum around. So it can move up to here and stop, or it can move up to there and stop. Right? So there is a chain where electron moves more or less freely. It wants to sit. Well, actually, it's more than one, but electrons want to sit on this chain, but they are restricted. They have kind of walls preventing them from going outside. So what's the class of materials? You see, this pattern is repeated. So it is
Crystal.
polymer. Well, crystal if 3-dimensional, if 1-dimensional, and if we are in presence of chemists, we should tell polymers.
Okay.
Okay? So it's polymers. But if forget science, physics, chemistry. Assume some country which is not good, like, or government is corrupted, laws are not followed, and in order to arrange things, those who the government is saturated not through elections but through some gray areas based on the income. So like, those who have more income just crawl into the power, and there are very few, let's say, families that control the country. So the power by few. Is there a bad word to call this situation? It was in the ancient Rome in the transition from republic to empire. It's like, you know, there is a republic, democracy, empire, and there is another form which is not stable on the global scale, but it is literal transition is power of few.
You talking about an oligarchy?
Yes. Did you hear this? Oligarchy. So, archy means like importance first or power. What does it means? O-L-I-G. Yes. So now back to chemistry and science. If you have one monomer, it's molecule. identical. If you have infinite number of them, it is polymer. What if you have few, like 2, 3, 4? Yes. Oligomers. So oligomers, not everything, oligomers. But those are not any polymers, not any oligomers. The main feature for them is that there is a conjugation. So instead of doing the single double, you can do this 1.5 bond, right? Just here. So one can do dash line, meaning that we do not know exactly where electron is. And it means there is a conjugation. So the name for those are conjugated polymers or conjugated oligomers. So conjugated oligomers. Conjugated oligomers can be described by a model of particle in the box. So we are slowly approaching true life. And this, how would you call this? Something like polyacetylene, transpolyacetylene? No?
Yeah.
Well, you can help me in the next meeting. My original background is not in chemistry, so do not take my word for this as a last ultimate truth, but I think is example. But this is the simplest possible. There are other molecules, other conjugated oligomers that can be described by a concept of particle in the box. Let's place here. I may skip writing them. So, like, it can be benzene rings matched to each other. Like, benzene, naphthalene, anthracene, and then I'm lost in the language, but acids. Right? And if they have fixed lengths, it is very appetizing molecule to describe as a particle in the box. It could be something like, well, I don't know what the name is nitrogen, but if there is a 5-member ring with sulfur and polymerized, what's the name?
With the ring with the where the nitrogen is the pyridine ring.
Pyridine ring, so polypyridine. And if there is a sulfur going in the repeated unit this way, will be polyethylene, right? So those are very popular materials, and one can do any electronics out of them, like computers, like flexible computers, flexible displays, flexible light-emitting diodes. There are challenges. It is not our main technology by now, but it is developed. So it was one area, very close to the hearts of chemists, like true chemists. But if you are in physics or material science, or if you are in colloidal chemistry, in organic chemistry, there is another class of materials where this particle in the box can be really good model to describe a lot and to get a lot of insight. Suppose that we do have a material where electrons feel itself comfortable, like material A, and material B where electron can be uncomfortable. Could be vacuum or something. A can be semiconductor, B can be either vacuum or dielectric, and then soon there will be lunchtime. So we can do sandwiches. Meaning you set up layers. layers to these materials, and then at least 3 layers. B, A, B. And I'm not designing anything myself now. It is what is already working in as a base for most of our technology as civilization. So thin films of semiconductors and dielectrics. So all CPUs, most of laser pointers, what else? Solar panels, they are primarily based on the thin film technology. So if there is a very thin film, delta Z is approaching 0, few atoms length, then in the, let's set up system of coordinates. X, Y, and Z. So in the, let me choose another color. So our poor electron likes to live in material A, but as soon as it hits the material where it is energetically unfavorable, it is turned down into other direction, then reflected again, and it's like jumping between walls. Therefore, it's like particle between walls or particle in the box. So it doesn't mean that it is not possible to go through the walls, but it is very energetically unfavorable. Therefore, at most excitations, at most conditions, the electrons are confined within selected material. Very good word. Confined motion. So the motion is confined between walls. Confined. Good word. Yes. So one can make nanostructures of materials, and with metals it is more complicated because there are too many electrons. Semiconductors are most suited for this concept.
Okay.
So thin films is the primarily type of systems where this concept can be applied. But in addition to thin films, which has 2 dimensions of free motion. So thin film is a 2-dimensional material. But in addition, we have, thanks to Braden, 1-dimensional materials like carbon nanotubes or nanowires. You can grow like a stick, a rod out of semiconductor. It also will be particle in the box, but it will be shape. Or one can grow colloidal structures of spherical or like cubic shape, and then it will be also confined motion of electron there. Colloidal particles. Nanoparticles. 2D, 1D, 0D. 2D thin films, 1D rods and wires, and 0D is cages, quantum dots, nanocrystals. Make sense? Yeah, I already drew this picture. So some of you may still keep a little skeptical view on this, because very soon, before end of today's meeting, we will model these complicated nanostructures with extremely simplified model, is as simple to the level of silliness. And a skeptic inside you can tell, like, it's not possible to describe so complicated system with so simple approach. So I want to give you atomistic argument for this concept. So in the spring 18, there will be offered a computational chemistry course, which will allow to model any materials on the atomistic level, predict properties not through boring equations, but just by pushing the button and getting the answer. And one of such modelings, so you've got a handout, and it is an example of a modeling of a thin film. So of two materials. Material A is a crystalline silicon, so not polymer, crystal of silicon, and which is semiconductor, and outer layers are silicon dioxide. Silicon, and here and there it is silicon dioxide. So the red spheres, if you see colors here, are for silicon, and the blue spheres are for oxygen. And if you draw lines between them, you see that just by naked eye that the structure is a little different. So what one can do, now we are not going into details because it is from completely different course. What one can look for electron which has highest possible energy when it is still there, so-called highest occupied molecular orbital, and look how is it distributed in space. And there are no cheesy tricks. It's just bold, plain computation. And these lines show the clouds here show three-dimensional distribution, and lines here show their projection on the z-axis. So you see that the solid line, the electron on this highest occupied molecular orbital is localized only in the space region which is filled by silicon crystal, semiconductor crystal. And when there is a dielectric, the probability to find an electron drops very close to zero. In order to make electron to penetrate into this dioxide, one needs to excite it by like 8 electron volts, which is like heavy UV. It's not practical for our regular electronics or chemistry experiments. So it's a big energy. It's possible, but it is hard. I thought I have enough supply. It was done by one of the students who took the course, but I have only a couple of preprints left. You can pass it over, and 2 of you can keep it. Decide yourself who. Okay. Any questions about general ideas, justification, and concept of particle in the box? Does it look more or less reasonable? So it is not ideal. It is not. If you look back, I probably skip. Here there are features of individual nuclei. And if one would make a potential here, the attractive potential that would keep electrons here, it will have spikes. The potential would look same as we did a few slides ago. But as an approximation, we can, and because we cannot do much right now, we can assume that it is just very simple flat potential. And also, from mathematical point of view, if the height of this potential is about 8 eV for this case, let me write an equation. 8 equals infinity. Right? It's convincing? Just 90 degrees. So we assume that potential is infinite. Today I'm most convincing. So the mathematical formulation of the problem will be as follows. So we know this whatever third way to predict future, where we need to solve the time-independent Schrödinger equation, get the basis functions, and then describe anything with time-dependent. But for time-independent Schrödinger equation, we need only one component to start solution. We need Hamiltonian, right? And for Hamiltonian, we need kinetic energy and potential energy. So kinetic energy is always the same, especially if we are in one dimension, and if it is a mass of electrons, d2 dx squared. But potential, it is what differs, which makes difference between one and another quantum problem. So after half an hour talking about realistic systems, now we want to set up simple enough potential that we can plug into Hamiltonian and address by all our strength and power to solve eigenvalue problem for such Hamiltonian. So since, and this is means we need to choose potential. So we are going to set up system of coordinates. We need to set up the size of the box, and we can tell the box starts at 0 and ends at x equals L. It's our free choice, where L will be whatever, 5 nanometers. You can imagine a conjugated polymer, which is 5 nanometers long, or you can imagine quantum dot, which is 5 nanometers diameter, so typical size. And then this axis will be v of x, or we can call this variable z. Probably I will do this later. Instead of dipping down to infinity, let's choose that it will be 0 between the borders, and then it will go to 8 electron volts, which we approximate as infinity. So the potential is very high, infinitely high, outside of the box. Okay? That's it. Now we stop being scientists and we become mathematicians. Well, this is the simplest part of the course from mathematical part. I'm sure that I can just stop and let you solve it, but to entertain you, and because the problem is so simple that I can do it, I'll probably go through all the steps. And if we will be short in time, we just continue on Monday. But it is really something that is easy to get. So you already discussed Schrödinger equation with potential, and if you want to be rigorous and we want to again send a postal dove to a friend on another continent, instead of drawing pictures, we can record it as potential is equal 0 in the range when the variable is between 0 and L capital and infinity otherwise. So the function that we are, well, we need to find set of eigenfunctions and values of eigenenergies. Since potential is infinitely high and electron has a finite energy, it is not possible, or it is from intuition, it will be very unlikely that electron will climb to the space outside of the couch, to this infinite potential. So we expect that it will be 0 outside. But inside, we do not know. We need to solve what is inside. How do we call, or how people call such kind of problems in differential equations? It's a very standard problem that I can make a bet that if you are taking, or if you were taking differential equations, you've heard this word, or these two words.
Boundary value?
Yeah, boundary conditions. So among, we do have, so this Hamiltonian times unknown function equals general equals function. This is differential equation because there is a differential operator. And one can find functions that very broad range of functions that should match this equation. But even remove the potential because it is simple. But then there are specific conditions on the borders of the range of interest that narrow down the set of functions. So if we know nothing and want to browse Wikipedia to get a guide for solving this very simple problem, we will definitely solve it without any mental concentration. You should look for the keyword of boundary conditions. Boundary conditions. So sweep over this slide, do not concentrate. Just in case some of you are mathematically picky, then I'll tell within 15 seconds. If not, just wait until I tell done. Solving differential equations is not science, it is art. The legitimate way to solve differential equations is just guess an answer and prove that it is correct. It is true. If you do it in your exam on differential equations, no one will object. But select a right guess function is an art. The most simple and general function is exponential. Exponential as function of your argument. And with this slide, one can prove that for our class of problems, it should be, if you choose an exponential, it should be exponential with imaginary power, where imaginary unit times some rate times your argument. Let's skip it for the sake of time. Now, no one was objecting that a guess function can be chosen as e to the power I, some rate times z, where z is our independent argument. I just swapped from x to z. In fact, it is only one function that we know from the previous part of the course, and we know the name of this wave. It is a which wave? Adjective. Yes. I was going to say round wave, cylindrical wave, plane wave. And intuitively, the wave can propagate left or right. If our box is symmetrical, we do not know. We will go to left or to the right. So we can add together waves that go into opposite direction. So we are not solving in true mathematical sense. We are just guessing, making educated guess, and then we will see if it matches the problem. Now, some of you were laughing when I told that you can guess answer. There is nothing ridiculous in this. You can guess general functional form of the answer, but you know, for the same function, you can change its shape a lot by tweaking the constants that are hidden in the parameters. So here we can tweak this rate, wave number, and then it will be denser fringes or more sparse fringes, which corresponds to quicker, slower wave. And also, we don't know in which proportions these waves are coming to our solution. So our solution should also have some expansion coefficients, which I suggest to select as C plus and C minus, unknown coefficients, plus, because here is a positive exponential, here is negative. So we are going to plug this functional form into time-independent Schrödinger equation and see what happens. Our tactical goal is to find the values of these coefficients and the rate. If you do not come to absurd nonsense, but come to some reasonable values, then the problem will be solved. Make sense? As a plan. So you take function that we guessed with our intuition, then plug it into equation with boundary conditions and see which of these functions will match. Will match boundary conditions. So the boundary conditions means that the function at the edges should be 0, and the left edge, right edge should be 0. And what is further outside is not our business right now. We're just not curious. We know it will be 0. Also, as soon as we find the function by analogy with our simplified world with only one electron and plane waves, we can plug in this wave vector into expression for kinetic energy and assume that it will be energy of our solution. So there are no more fresh ideas. The rest is boring math. How are we doing this time?
1 minute.
1 minute. Okay. So make some mark that we should start from here, and I will just maybe sketch the path. But there is no time to do it slowly. I just sketch so that you have some seeds of solution. So general form, then we are going to replace exponentials according to Euler formula. And then you'll see that there will be two pairs of terms of same function but different coefficients. So what one can do is to combine same functions with different coefficients and use this as a functional form. So there is only imaginary unit here. And then this expression is plugged into what? Into boundary conditions. So by plugging this expression into boundary conditions, we will find symmetry between unknown coefficients, and we will follow the properties of trigonometric functions that will allow us to find the values of wave vector. We could squeeze all this here, but let's finish. So, mission complete for today. I look forward to enthusiasts to visit evening session. And if you are not among them, then just do not forget to send slides by Thursday evening.
Just
But did you say